Welcome to Secure Software Development. We're going to begin as usual by talking about object linking and embedding. This is a basic idea. It's been around for a long time, but you don't want to put every single thing in a document. And you may want to have a spreadsheet that's in a text document actually be a link to a spreadsheet that you can edit in a spreadsheet program. And you may want to have an image be something that's downloaded from the web, maybe whenever in real time. And so all of these things lead to this idea of, hey, I'd like to build links into my document. And these slides, for example, have links in them, in this case to YouTube videos and other resources, right? I mean, the slides, these Google Slides themselves, they all link back to resources stored at Google in order to make all of this work, fonts and animations and all of that. So let's take a look at one specific instance of doing this. If you go into Word, and in this case I've done this on a Mac, but it works on a PC as well. If you go into Word and you switch to the Insert ribbon, on the Insert ribbon on the Mac, it's just you directly click Field. On Windows, I think you have to click one other thing and then you click Field. So you want to insert a new field. When you do that, you'll get this little dialog, and you want to go and find Include Picture. So we go and find Include Picture. We include the picture by URL, and we include a /D in order to tell the system, hey, I want to be sure that you fetch the most recent version of it. We're done, and now look, I have an image. And in this case, I'm pulling an image from a website called thispersondoesnotexist.com, which uses an AI to generate a brand new picture every time you visit it. So if I close this application and I reopen it, I get a new picture, right? A new image was downloaded just for this. And that illustrates, a pretty powerful idea, right? I'm seeing what the current state is of that website. Part of my document is something that could change anytime I open it or print it or look at it or preview it. I'll get a new image in there. The thing that we're connecting to in this case was an image, but it doesn't have to be. It can be almost anything. In fact, you could embed HTML in there. And HTML can contain almost anything, including JavaScript. And once you have JavaScript in there, JavaScript can do almost anything. And in particular, it can manipulate the document object model of a web page. In this case, the document object model of the included HTML, which is then rendered as part of the document. And that's kind of a neat and perhaps also slightly scary thing. So let's see an example of that. So I might have something like you see over on the right. Here I've got a little script. It's a little snippet of JavaScript. I go and get an element by ID. I get the picture of Brendan Eich over there. And if you don't know who he is, look him up. And then I go ahead and change the source. I change the title, and I modify the image caption. And so when I open the document, I write the document, it has this stuff in it, and you might scan the document and see this stuff. But then when the document is opened, the JavaScript runs, and we've replaced that JavaScript with the much nicer Python and an image of Guido van Rossum. If you don't know who he is, go look him up. So that implies that I can do some kind of unusual stuff in a document. So let's switch gears and let's talk about the Microsoft Support Diagnostics Tool, MSDT. What is this? Well, when I have a problem, and it's a problem with some Microsoft stuff, I want the best support. And I don't want just someone telling me, hey, turn it on and turn it off and turn it back on, jiggle the cord. I want something to get on my machine and fix the darn thing. So that's what this tool allows a Microsoft professional to do. It allows Microsoft support personnel to gather information about your machine, right? What kind of computer are you on? What software do you have? Because maybe the problem is an incompatible library or something else like that. So to diagnose it, they need information. This tool will collect and send them that information. And then in order to fix things, they might need to run software, edit the registry, do other things like that, and this tool can also do those things. The idea is you contact support and they say, hey, run msdt.exe and run it with this given passkey, and that will then allow us to diagnose your problem, to work with you, to fix it, and get you back and going again. Great tool. So then in the 27th of May, 2022, a message got posted to, at the time, Twitter. And it's kind of interesting. It says, interesting maldoc, malicious document, was submitted from Belarus. It uses words external link to load the HTML and then uses the MSDT scheme, there's that MSDT, to execute PowerShell code. So let's zoom in on that little snippet of text there and see what's in it. And so you can see we're doing JavaScript stuff. Window.location.href. Right? That's setting the content of the window. And it's setting it to something obtained from this MS-MSDT protocol. So, unsurprisingly, you want to be able to have people fire up MSDT instead of telling them, hey, push window R and run this tool with this thing. You just want to send them a link and say, click the link. And so, sure enough, there's a link to click. And that's the type of link we have right here. And you see some stuff after it, some options that get passed along to it, and then a big string of gibberish. So here's what's basically going on. When you open this document up, it's going to download some HTML. The HTML is going to contain some JavaScript. The JavaScript is going to open a URL with the scheme ms-msdt. That's going to launch the MSDT tool, and in this case, it's going to run untrusted code. Wait, untrusted code? Where was that untrusted code? Well, we'll see it in a moment. If the document is in rich text format, RTF, it turns out previewing it can run that code. You don't even need to open the document. When it generates a little preview in the file browser, it'll run the code for you then. It's very convenient. Let's go back to this and let's ask the question, what is this gibberish down here at the bottom? If you take a look at it, you'll see that it's a string being added together and a whole bunch of junk in there, and you'll see that from base 64 at the beginning, right there. This is just a way of hiding the content of this string. It's a base 64 encoded string, and we can decode it. When we decode it, we get something like this. We see that we're starting a command.exe. Our window is hidden, right? Window style hidden, just hides the window. And there's a whole bunch of other stuff in there. I don't want to get into all of that, but you can see what's happening. I have a little bit of obfuscation. So I want to scan the document. So I scan through the document, but the document contains code that runs that modifies the document. So my scan of the document for bad stuff may miss it. So when that code runs, it then unpacks this stuff and is able to then run this untrusted code. So this vulnerability gets a 7.8, right? Again, not an Olympic level vulnerability, but not an easy, nice one either. This is fairly serious. This is remote code execution. It's not a privilege escalation vulnerability, right? It runs the malicious code as a normal user. And as a result, nothing could ever go wrong because normal users don't have all these privileges, right? Well, yeah, it's still a problem. Because the file used had this name that ended in 0438, and because 0438 was the area dialing number for Follina, Italy, the vulnerability was dubbed Follina. And there you go. If you want to know more, I've gone through this pretty fast, admittedly. There's a really great article to write up right there. And if you'd like to see an exploit for it, you can go ahead and take a look at that second link. Be aware, there are programs that can take an action on behalf of a user that user might not be aware of. If I send you this Word document that has this external link, you might not know that external link is there. And if that link points to something that I control, maybe I can at the very least see that you've opened the document, or at least previewed it, and perhaps send different content based on what I want to happen as opposed to what you want to happen. We're going to revisit this in a little bit. So what are the implications? Well, again, we have to go back to that initial statement that we keep saying over and over again. All systems are vulnerable. If you create a way to link to another system, so I've got two systems, and I figured out a way to link them together. I got my database over here, my word processor over here, my spreadsheet program over here, my web browser over here, and I'm going to plug them all together. What I'm basically doing is I am running the risk of importing the vulnerabilities of one system into the second system, or any other system I'm connecting with. But in addition, when I plug them together, I have the risk of creating new vulnerabilities because of the interactions of those systems. By themselves, they're fine. But when you plug them together, you create a new path for that vulnerability, right? MSDT was fine. I had to run it with this string that I got from Microsoft Help. Great. I was explicitly running it. Grabbing images in the Word document, possibly a problem, but not that bad. But when I combined the two together, right, it was just like when I combined the Log4j stuff, right, with the ability to deserialize information, right? Go out and get information out of some public or some internet-based database. When I combined those two things, I had a vulnerability. Same thing here. Sorry, I'm very tired. So let's talk about cyber-physical systems. We're going to spend one class on this. The basic idea here is I want you to have seen the ideas, heard the words, at least have heard the terms once, because this is becoming more and more common, and I would like for you all to know a little bit about this topic. So, all computers control physical assets. If someone says, oh, the difference is these things control physical components, all computers do that, right? Your computer has fans, and it controls various devices, various physical devices, and it has physical inputs, right? That's true of all computers. The distinction between what we would think of as IT devices and what we would think of as what we're going to call OT devices has to do with context. Everything is context driven, and it's driven by the purpose of those devices. So over here on the right, that blue box is a pencil case, which is mounted on one of the support rails for a garage door opener. And it contains a couple of things. You can sort of see in the picture, this little guy right here, that's a Raspberry Pi Zero, probably way overbuilt for this particular purpose. And then down here below, we have a pair of optically isolated relays, and the Pi controls those. And what this is a way to control a garage door opener, in this case using a Raspberry Pi Zero, which has Wi-Fi on it and allows you to open and close and check the status of the garage door. So in this case, This is a computer that is built not necessarily to do computing, but with the express purpose of controlling and monitoring a physical asset. And we tend to think of this as an Internet of Things type application. When we think of cyber-physical systems, we think of something whose focus is the control of physical systems and their physical effect. Now, over on the right, we see something much larger. This is part of the heat management system for the Summit supercomputer located at Oak Ridge National Laboratory. It's a big system. It produces a lot of heat, and this is just part of the system for managing that heat. It's actually a very efficient system. It can run stuff around a loop to cool it down. If that's not sufficient, it can pump it up into these cooling towers. And if that's not sufficient, it can run the fans. If that's not sufficient, it can actually run the chillers. But it can make those decisions based on the ambient conditions and the temperature of the water coming off the system and be very much more efficient. And to make all that work, you need computer controls because you have to know, I got to open this valve, turn this compressor on, I have to turn the fan on, I have to do this or do that. I have to monitor conditions, right? What's the outside air temperature? Because that affects the way in which the system works. We've got to monitor all that. In addition, there's diagnostics, there's maintenance on it. It's a fairly complex beast, and so it requires some complex computers and software to monitor and manage it. The focus of the system is the control and availability of a physical asset of the system. The purpose of the power grid, for example, is to deliver electricity. Now, we could do that, and we did it for years without computer control. Okay? We could run this thing without computer control. We always run the whole thing, run the chillers, the whole 9 yards. We could do that. But we can do a better job if we put some computing around it. So these are things that we could do without computers, but we use computers to make them more efficient, to make them more responsive to real-time conditions and changes in conditions. So let's sort of line up the distinction between IT and OT. So IT is primarily about information, right? Information technology. It's about the flow of information, processing information, generating information. And IT applications are typically the kind of thing that you have to have a computer to do. You can't do without a computer because really the focus is on the computation itself. Over on the OT side, we are talking about the flow of materials or a physical effect, much more than just the data itself. The data is sort of a side effect of doing that. OT applications generally can be performed without a computer. They're not dependent on it. And they tend to arise by trying to make a system more efficient, or by removing a human from the control loop, or maybe centralizing stuff. Okay? So that's the basic distinction. It's not a perfect distinction, because when we look at the systems, when we start to dig into them, they tend to look very similar. The power grid, right? This big thing that keeps the lights on here. Wow, that's this thing with these big transformers and these switch yards and these substations and power lines stretching over miles, carrying power, and also routers and switches and computers and that basic set of stuff. If you think about the accounting and billing part of the power grid, right, that's going to have big machines, big computers tied together with routers and switches and all that stuff. The same kind of infrastructure as the OT side of the grid. They share a lot of the same stuff. And so the distinction comes in because of the mission of those systems and what you're intending to try to do with those two systems. So, and manufacturing, power grid, chemical processes, all these things are typically going to have an OT side focused on controlling and managing a physical process for its physical effect. And an IT side, managing the data that's associated with that, managing billing, access controls, those sorts of things. An industrial control system, ICS, is a cyber-physical system that controls an industrial process. And that could be any industrial process, manufacturing, power distribution, could be keeping the lights on in a building. The example over here at the left is part of a control system for a crop irrigation. And it contains a lot of the same things that you would see in a power grid. It contains sensors, it contains data loggers and historians, it contains specialized stuff like solenoids to turn the water on and off, flow meters, moisture sensors, all of these different little pieces. So I mentioned critical infrastructure, and in the U.S. we tend to divide critical infrastructure up in this way based on something called the Presidential Policy Directive 21, and there's a link there to it. And that directive defines 16 critical industrial sectors, and it gives a sector-specific agency with oversight of each one. And you notice a lot of these say DHS, the U.S. Department of Homeland Security, and CISA, the Computer Information Security Agency. And so you can see chemical, commercial facilities, communications, critical manufacturing, etc. If you'll find a few of these are a little different. What we would call the DIB, the Defense Industrial Base, DOD has oversight of that. Energy, that's DOE, the Department of Energy. The Treasury has oversight of the financial stuff. Food and Agriculture is the U.S. Department of Agriculture and Health and Human Services. Healthcare, that's also Health and Human Services. And down there at the bottom, water, that's the Environmental Protection Agency. Above that, you see Transportation Systems, DOT, Department of Transportation, and DHS, the Department of Homeland Security, have oversight of that. Planes, trains, automobiles, what have you. All of these have something in common. They are all examples of industrial control systems. They have industrial control systems throughout them. Every one of these sectors is heavily dependent on computers and the associated software. So let's talk about some common ICS components and concepts. Hopefully you have an idea what ICS is now. Let's talk about some of the pieces that are used to implement it. The main component, and the one that you'll most commonly hear about, is the programmable logic controller. So in the early days, before we were putting computers into everything, you still had to have control logic. And that was often implemented with relays. And so you had relay logic. And you can build very sophisticated things out of relays. You can build Turing-complete systems out of relays. So the PLC makes that relay logic programmable. So instead of having to wire them together, if there's a change, I have to go in and rewire all these little relays. I can instead create virtual relays as a computer program and then use those in this programmable relay logic controller, a PLC. And it's just an industrial computer with inputs and outputs that are specifically designed to read from sensors and write to controllers. PLCs are typically programmed, not necessarily with C or a language like that, but with ladder logic. Okay? Ladder logic is very similar to relay logic. Sometimes they're programmed with something called structured text. If you want to know how PLCs are programmed, you can take a look at IEC 61131-3, which is the standard for this. There's a good discussion of relay and ladder logic at that link. We'll have a short one here in just a minute, so hang in there. If you've never heard of ladder logic before, we'll give you a quick refresher of it, or a quick overview of it. Another main component is the HMI, the human-machine interface. This is the component that lets you interact with the system. Usually it's a touchscreen attached to the component that you're interacting with. Video over on the right-hand side, tell you more about it. A remote terminal unit, or an RTU, is very similar in many ways to a PLC. It's basically like a ruggedized version of a PLC. It's a little more modern, and so it has some additional programming options. For example, you might program an RTU using C. It might provide a Linux environment, which maybe is more familiar, and you can use other programming options for it. RTUs often have advanced software, and they support a lot more stuff just out of the box. This requires more capabilities for the device, and so RTUs, because they're first ruggedized and second a little more powerful, are often more expensive than PLCs. There are other options as well. A programmable automation controller is sort of an intermediate step between the two. And so what's the hard and fast distinction between a PLC and a PAC and an RTU? There isn't one. These are things that grew out of marketing, right? You had your PLCs, and I came along and said, hey, my PAC is a little more powerful than your PLC. And somebody came along and said, my RTU is more powerful than your PAC. Fine. A programmable logic array is basically a step down from a PLC, right? I basically am just telling it how to wire up the relays. and I have sort of a weaker set of options associated with that. And it's meant to be programmed only once. So I create this array, and then I put it out into the world. In a way, it's like the distinction between an FPGA, which I can reprogram, and an ASIC, an application-specific integrated circuit that is purpose-built and used for that specific purpose. For the most part, you just need to know that a PLC is an industrial controller programmed with ladder logic, and an RTU is a ruggedized industrial controller with maybe a wider range of options. A few of the things that you might run across: a master terminal unit is a tool that consolidates connections to a bunch of RTUs. An intelligent electronic device. Unfortunately, the initialism is IED. You'll hear people in the power grid talk about IEDs. They mean intelligent electronic devices. They very seldom explode. Is any device that collects data, can do some processing, and communicates with other devices. It's just what it says in the name. It's an intelligent electronic device. And then finally, a very important piece, a data historian logs process data periodically within the environment. So when you change a set point, it'll log that event. When there's a sensor reading, it will log that event. Doesn't necessarily log them all. It may give you a somewhat coarse record, but it gives you a record of everything that happened within the system. That takes us to SCADA. So SCADA is another initialism. It's supervisory control and data acquisition. The key word in that is supervisory. So who is the supervisor? Well, there's a human in the loop. SCADA is not intended to be fully autonomous, but provides control at the supervisory level through a HMI, which provides you with information and also with the ability to affect some control. Okay? So SCADA has a human in the loop, right? There's someone in there who can go and change set points or do some other stuff with it. An example of a big SCADA system is our national power grid. People sit in, for example, for TVA, the Tennessee Valley Authority, which is our local power transmission authority. People are down in Chattanooga, Tennessee, and they do load balancing. They can open and close floodgates of dams from there, and they can buy and sell power and do all the other things you need to do to keep the grid balanced. It's not a fully autonomous system. There's a whole bunch of people in that room making decisions based on the weather, projected demand, the prices of different sources of energy at the time, the availability of things like headwater at a dam. They're putting all that into their heads and then making out a plan and then executing that plan and using the SCADA system to do it. It's distinct from another kind of system called a distributed control system, or DCS. And that's typically what we would call a closed loop control, right? SCADA has an open loop with a human in there, right? So commands go out, sensor readings come back, but they don't close the loop. The sensor readings don't directly affect back to where the commands are. There's a human being in there seeing all this stuff and taking action. And that was what makes it supervisory, a SCADA system. A DCS system, we close that loop, and it operates entirely automatically on its own. And an example of this is components within an electric substation. They operate entirely on their own. And you may say, well, that's just a part of this bigger energy distribution system, and that's right. SCADA systems and DCS systems can work together. So at the top, I have SCADA, but I can't control every single little piddly device out there, right? I mean, I'm not standing in the control center in Chattanooga and saying, I'm going to change this recloser on this pole somewhere out there in the world. No, I expect there to be a system that manages that for me. I, from here, could change set points in there, do other things to it, but once I've got it running, it's going to take care of that stuff for me. Okay? So DCS can handle some of that lower level stuff, and then I, as the supervisor, handle the higher level stuff. So they work together, right? SCADA systems gather and present data to supervisors, and they make decisions. DCS provides distributed autonomous control over some complex process. And like I said, often large SCADA systems are made up of smaller DCS components. So let's do a little aside here, and let's talk about ladder logic. It's an aside, so I'm not going to expect you to understand all of this, interpret all of this, know all this for the exam. I just think it's worth talking about. It's helpful if you've seen it. Ladder logic is a rule-based programming language, and it grew out of relay logic. And we call it ladder logic because what you see over on the right-hand side looks like a ladder, and that is, in fact, a ladder logic program. And it looks like a ladder, right? It's got these two rails, one on the left, one on the right, and then a bunch of rungs that connect them. And that's what we call them, right? There are rails on the left and right, and then there are rungs. And each rung represents a single rule in our program. And the rungs execute the way that we here in the United States and in many other countries would read, and that is left to right and top to bottom. Okay. So we can think of the left rail as providing power. It's a power source. And the right-hand rail as being the power sink or the return. And so we can think of current as flowing across from left to right across each one of these rungs. And so, for example, if there's a switch on the left-hand side of the rung and a light on the right-hand side of the rung, closing that switch would turn the light on. Opening that switch would turn the light off. Hope that makes sense. And we typically represent it exactly that way. We have things that sort of traditionally have square brackets, and we think of them as contacts. Could be different kinds of switches, right? Could be a push button switch, could be a switch, a toggle switch, a PSPT, whatever you've got, it's something over here. And then with the round brackets, that represents a coil, like a motor coil or a light. And so typically the square brackets are inputs. The rounded brackets are outputs. And by convention, we put the inputs over on the left, the outputs over on the right. And that's how we organize it. I mean, if you think about it for a second, go back to my example of the switch and the light. I could put the light first and the switch second, and it would still work, right? I close the switch and current flows and the light turns on. I open the switch and current stops. So the order, might seem a little arbitrary, but because it's a program executing in a certain way, the left to right is important. All right. Over there on the right-hand side, we have run and motor labeling those two things. And those are variables. So run is a Boolean variable, and motor is a Boolean variable. Run could be, let's say, true or false, true indicating it's closed. Motor could be true or false, true indicating it's running. So, for example, with this example, if the run switch is closed, then motor over there is enabled and becomes true. And there are different kinds of variables. There's Booleans, bytes, words, D words. It's a whole collection of them. Here are a couple other little examples. So here we see an AND over on the left-hand side. If run and go are both closed, then motor can activate. If either one of them is open or both of them are open, motor will not activate. Over on the right, we see an OR. If run or go is closed, then motor can activate. If both are closed, motor will activate. But if neither are closed, motor is not enabled. In addition, we can have something kind of akin to negation. So over on the right-hand side, we put a little slash in there to indicate that stop is normally closed. So what this would tell us is that's a normally closed switch. So when I activate it, I'm actually opening that switch. So motor, we'd see, would be running until I activate stop, at which case motor would then stop. So it's like a knot. And we can combine them. So over on the right-hand side, we have the normally closed stop switch and the normally open run switch. So when I close that run switch, the motor will turn on. And then when I want to stop it, I could push the stop button, which would then open it and kill the motor. Hope that makes sense. And we can pull it all together here, and in fact, we can add a few other little modifiers. So here I'll put a P inside the run there, meaning it's pulsed. So it's now a transient. And you'll notice that motor actually labels both an output and an input, or both a coil, right, the little round thing over there, and one of these little switches over here. Let's see what that does. So stop is normally closed, so we can ignore it for now. If I push run, push it, then it's closed for the duration of time that I'm holding it in, right? It's pulsed, so when I release it, it's going to release and open again. But I push it, current flows all the way over here to motor, which then turns on. And then when I release it, what happens? Well, you'll notice motor also labels this other input. So when motor over here turns on, that motor over on the left closes and provides an alternative path for current to flow to motor. So I push run, and that basically latches the motor value, which keeps it running after I've released the switch. When I want to stop it, I push stop, which is a normally closed one, so that opens stop, and that interrupts and stops the motor. Here's some other examples. In this case, I'm using some Allen Bradley logic of set and reset. So both run and stop are pulsed. When I push run, I set motor, which means it just starts running and stays running. When I push stop, I reset motor, meaning I turn it off, it stays off. Okay, even though those switches are transient, they're pulsed, the set and reset mean that the change is persistent. There are blocks for doing math, comparing values, for timing, for counting, and it turns out, probably not that surprisingly, that ladder logic is Turing complete. There are some standards. Like I said earlier, inputs are near the left, outputs near the right. We only include one output per rung. We could do more, but by convention, we want to simplify things and make it more manageable, so there's one output per rung. Inputs can be connected in series, parallel, or a combination, as we've seen. While input devices can be represented multiple times in the diagram, each output device can only be represented once. That's interesting. That means I could have the same input device labeling multiple rungs, but I would have a particular output device just on a single rung. That's interesting. Is that always the way we do it? No, it turns out it's not. Let's go back. Here, for example, I have the output motor in two different places because of the set-reset properties of the Allen Bradley language. All right. Input and output devices are horizontal, left to right, top to bottom, etc. So let's talk about ICS, or Industrial Control System Networks. So this is a very simple model. I build my system. I have an HMI. It connects to a PLC. The PLC connects to some physical process, and I'm done. Right? The PLC reads sensors from the process and controls actuators in the process. It presents that information to me on the HMI so that I can then take some actions. Start it, stop it, change set points, etc. And the system is not connected to any other networks. It is what we would call air-gapped. Right? It's air-gapped. There's no other external connections. The important thing to know about an air-gapped network, the thing you should keep in mind when you're thinking about air-gapped networks, is that it's a myth. That basically you should presume that every network is connected to something else, either directly or logically, because people will come along and plug in their laptops to do work, or they'll plug in data thumbs to transfer data. You should assume air gapping is a myth. You'll still need protection on it, even though it's quote-unquote air-gapped. Never depend on it. The first rule of gun safety is to assume a gun is always loaded. First rule of network safety is to assume all your networks are connected. So the thing to know about air-gapped networks is there's no such thing as a truly air-gapped network. So here's another design. This is a flat network. Basically, we have a firewall to protect us. And then we have some IT stuff like our email and our file server and some computers. And we have OT stuff. We have a process monitoring computer, typically an engineering workstation. We have an RTU, and then we have some controlled process. And we just run Cat6 and connect everything to a centralized switch, and we're done. And that's simple. It's easy to set up, pretty easy to maintain. There you go. We're firewalled. We're in good shape. Don't do this. A flat network simplifies things, but it also exposes all your OT systems to the same threats as the IT systems. Okay? And it creates better ability so that when an attacker gets in, or when a malicious insider takes an action, they can move laterally through your network fairly easily. That's bad. So don't do that. So we've killed off two models. Let's stop and ask, what do we want? Well, ideally, we'd like to isolate the OT, or operational technology network, from the IT, or information technology network. We'd like to isolate them as much as we can. I mean, clearly they're going to be connected in some way, but we'd like some kind of logical isolation. We'd like networks that are logically zoned based on sensitivity, criticality, and impact. And we would like to have security at all the boundaries so that we have some kind of active defense. That's all well and good, but ultimately, how do we organize the network? What zones do we need, and how do we implement it? And that takes us to the Purdue Enterprise Reference Architecture. In the 90s, it was a model for ICS networking, and the slide says security. I apologize. It wasn't really for security. It was really for lifecycle management. What do I mean by lifecycle management? Well, when I'm setting up a network for an industrial control system, I need to design the network. I need to figure out where the controls are, how things are organized, how I manage deployment, how I put new devices in, how I take old devices out, how I control this thing over the course of its lifetime. Lifecycle management for this network. And the Purdue Enterprise Reference Architecture was really about that. It divides an enterprise up into people, facilities, and systems. And then it gives you a system for master planning, design, and analysis of that network. It influenced some other standards, ISA 95 and IEC 62264, and all of these divide the enterprise up into a set of layers. Over on the right-hand side, you see at the bottom the blue layers. Those are your OT layers. Up at the top, the green layer, that's your IT layer. And you can see there's a layer that's sort of blended in the middle. That's the IT, OT, DMZ, or demilitarized zone. It's a place where the data from the levels below and from the levels above have to come together to accomplish the mission. So I have to blend the two in order to get some things done. The main security recommendation was to create these levels and isolate lower levels from higher levels. And if you look over on the left-hand side of this diagram, you'll see this little string of firewalls. So we come in, firewall. You want to go down to the DMZ, firewall. You want to go down to the workstations, firewall. Down to the HMI and the SCADA, firewall. Okay? So we are protecting each one of these as you move down. And so security achieved, right? That's the idea, right? We have security because we have firewalls between the layers. But let's take a closer look at this. In particular, let's look right here, okay? This guy is the engineering workstation. This is where I manage the configuration and the deployment of configurations for my RTUs and my PLCs and my sensors and all of the rest of the OT stuff. If I get access to that, it seems like the game's over. And so does this stuff down here need more protection? Right? Do my sensors need more protection than this engineering workstation? Feels like I've, in some ways, almost inverted my security, right? So maybe that's not the way I should be doing it. Another thing to note is that. What is that? Well, A jump host is typically a machine you use to get access to another set of machines. And you notice this provides me with this little dashed line. And what is that about? That's something interesting, right? That lets me get direct access from one layer jumping down into another. A little concerning. I'm not sure what that's about. The point of this is not a security architecture. And in a way that's okay. It wasn't really meant to be a security architecture. But it contains some good ideas. Okay? Segregate the IT and OT systems. Segment the network. Okay? This focused very heavily on preventing what we'll call north-south transit. So north being up at the top with the IT, south being down at the bottom with the OT. It tries to prevent that. It puts all these little firewalls in to prevent that. But it doesn't prevent east-west transit, right? Once I have breached a level, I am free to just spread across the entire level, right? If I can make it to the bottom, then I own the whole system. And that's really not what you want, right? You don't want all your most critical assets to be in the same layer here, because then there's no additional protections. So let's talk about some other models. Let's talk about NIST SP 882 and see a little bit about what's in there. This is basically a modified version of the Purdue architecture, but it directly tries to address security, and that's great. That's great. In fact, as you look at it, you'll see down here cybersecurity servers. You'll see all kinds of stuff in here, and that's wonderful. Look at this, down at the field level. There's your engineering workstation. Look how protected it is at the lowest level. But again, we're doing layers, and we're protecting each layer. And one criticism of this might be, where is the cloud? Cloud is increasingly important. How do I fit cloud into this? And once again, it feels like if I can move down, right, if I can get to that lowest level, then I own the whole system. So let's talk about IEC 62443. That's something I hear so often, I can just quote the number. 62443 is actually not itself just a standard. It's actually a collection of standards that work together. And it's not an architecture as such, but it's a way of determining what your security architecture should be. And it focuses on risk management in order to do this. If you'd like to know a little bit about it, there's an overview of the standards in that video over on the right-hand side. The standards are very comprehensive, right? If you were paying attention to the last slide, each one of these little guys here is a standard, and this is kind of a simplified view. There's a lot going on here. And that's because they're comprehensive, and the overall set of standards can be a little bit intimidating and complex. Basically, what's going on is we are managing risk, and 62443 uses this notion of criticality, right? How critical is something? Likelihood, how likely is someone to be able to successfully tamper with that? And impact, what is the impact of something bad happening there? It uses that model for risk analysis, and then it relies on least privilege to slow down attacks. So over here on the left-hand side, we have these little red things here. These are conduits. Conduits connect these different security zones here. And so you can see that instead of having everything at the bottom on the same level or same layer, I have broken things up so that now I have these little logically isolated islands, which are then connected by these conduits. Each one of these little islands is what we would call a zone. A zone is a logical grouping of stuff, right? Field devices, an HMI, PLCs. There's a switch here. There's different kinds of field buses, right? DMP3 and other stuff out here. And then there's a firewall to protect it. So a bunch of things that are connected logically and work together, and they have common security requirements. Remember the notion of a trust boundary? So this is kind of a set of things within the same trust boundary. Zones are connected by conduits, and those bundle the communications that have the common security requirements, right? So I've got one set of things here with a common set of needs, and then maybe a different set of things up here with a different set of needs, and then the conduit bundles the communications together for that. And I can talk about, what security properties do I need this conduit to have? What security properties do I need this particular zone to have? So, quick tour. One thing to point out is there's no system so simple it isn't going to be computerized. And as an example, I give you a link to how to build your own computer-controlled PAS dispenser, right? Why tilt the head back and take a candy out when you can program a little, a set of components to do that for you? All right. Now, as we went through all this, we talked about IT and OT and SCADA and DCS and HMIs and RTUs and all these other pieces. It may have seemed like some of those were a little bit fuzzy, and that's because they are. I've tried to draw a pretty clear distinction whenever possible, right? OT is about the control and management of a physical process for its physical effects. IT is about the control and management of data. But they get blurry because they use the same stuff, right? They're using switches and routers. And yeah, you need data in order to affect the control of the system. And yeah, the IT stuff also has physical things it controls. And so it's a little bit of a blurriness there. But a lot of this can come from the people who work in industry themselves. Sometimes people say SCADA as just a catch-all for computer-controlled anything. And that's okay, I guess. And sometimes they'll talk about SCADA and OT, and you're like, well, isn't SCADA really a part of OT? So those things can get a little bit fuzzy. I hopefully have given you some precise language around it, or a little bit more precise language. But if you encounter this out in the world and it seems a bit fuzzy to you, it's just the way those terms are used. And that's it.